We've spoken a lot about translations, but what about rotations? Well, generally speaking, convolutions don't, by default, have rotational equivariance. This is why in a typical convolutional network workflow, you often need to do data augmentation, which just means, amongst other things, rotating your input images so that the network can see the images from different perspectives. Now, in terms of an equivariance condition, we can write this down pretty clearly. So let's say I take my 7 from the MNIST dataset. If I do the convolution and then rotate the result in the feature map plane, do I get the same thing as if I do the rotation in the image plane and then do the convolution? Well, the answer, generally speaking, is no. So I've indicated that up here with this condition. F of g of v is, generally speaking, not equal to g of f of v. It is possible to derive the specific conditions under which this is true. So let's go ahead and do that. Let's firstly sort of establish the setting that we're working in then. So again, we've got some general scalar field, continuous function in the range -1 to +1. We've got our continuous convolution definition. And like I mentioned, the kernel is able to move, so it can scan the entire image. And the vector p tells you where the center of the kernel is, and the vector p prime tells you where you are inside the kernel. Now, for a rotational equivariance condition to be derived, I'm just going to use this vector notation, p and p prime. And I'm not going to worry about integration limits. I'm just going to write an integral over R2. And as you can see, the integral, at least in my opinion, it looks a bit pretty this way anyway, p plus p prime. And we'll integrate over p prime. And in order to go ahead and actually derive the conditions for rotational equivariance, we need a device called the pullback. This is really just a mathematically pedantic way of stating the obvious, if you ask me. All it says is that, let's say you take a toy image, like this S image here, and you rotate the image in the image plane using standard rotation matrix Q alpha. It says that you get the same thing if, rather than rotating the image, you just rotate the coordinates in the other direction. And so we can express that condition using this equation at the bottom. Q alpha of v, the rotated image, just gives you the same thing as if you express the image in the coordinates Q negative alpha of p. So that might look complicated on paper in terms of the algebra, but when you visualize it, it's just pretty obvious. We will use this in, I think, the next 9 or 10 slides. So that pullback definition is pretty important. So let's say we've got our toy image then. So I'm just going to use this little S. And we'll just define the convolution like we did before. It's just the image v times the convolutional kernel f integrated over the kernel offset vector p prime. So let's go ahead and rotate the image. So we'll write the image as q alpha of v, p plus p prime, times f of p prime, integrated over p prime. And we'll then use the pullback that we just derived, meaning that we'll go ahead and now write that as the same image as before, but in the rotated coordinate system, where the coordinates are now rotated in the opposite direction, in the direction negative alpha. So that means, of course, we can write it as v of q negative alpha, where the q negative alpha is applied to both p and p prime. That's because the kernel offset vector still exists in the image plane. We haven't done the integration, we haven't done the convolution yet, so that convolutional, that kernel offset vector comes along for the ride in terms of those rotations. And incidentally, I have used the notation q superscript -1 subscript alpha. I just mean q of negative alpha, right? The rotation in the other direction. Okay, so let's say we now go ahead and actually do that convolution. Well, we can denote where the kernel offset vector was before that convolution by just denoting it in this sort of darkened color here. And I'm just using this toy image to denote the convolved S, that little blob just there. So that represents one path in the equivariance condition, doing the rotation in the image plane first and then doing the convolution at the end. So now the obvious thing to try is to do the convolution first, which we can write down as follows, and then do the rotation in the image in the feature map plane and see what would be required in order for us to get the same thing in order to derive the rotational equivariance condition. All right, so I'm going to use this vector p double prime now to denote where the kernel offset vector was before the convolution happened. And I'm using p double prime just to denote the fact that it's now corresponding to the other pathway that we're taking, convolution first, then rotation. Okay, so we can write it as follows. Now let's go ahead and rotate that feature map. So we can do that, no problem. We'll just use the Q alpha vector, so the Q alpha rotation matrix, excuse me. Now the thing is, the convolution's already been done. We're in the feature map plane. So that kernel offset vector doesn't come along for the ride this time. But because the kernel offset vector is integrated over infinity, it's quite harmless to just translate it back to the end of Q alpha p, because the kernel was scanned across the entire image anyway, all the way to infinity, right? So just to make things look a bit simpler, it's quite harmless to just do a translation because we're integrating over all space. We'll then use the pullback again, and we're now going to rotate the coordinates using the Q negative alpha rotation matrix again. This time, of course, the kernel offset vector does come along for the ride, meaning that where the kernel offset vector was before now gets rotated relative to the coordinates, because we're rotating the entire coordinate system. So I hope that's clear. So we end up with this p prime vector, double prime vector now being slightly rotated. And we can then go ahead and move things back into the image and kernel plane in order to arrive at this expression. This is a fairly confusing bit of algebra if you don't have the diagrams, but because we've only applied the rotation to the convolved image in the feature map plane, and the kernel offset vector did not get subjected to that rotation, the integrand reads v of q negative alpha of p, where that q negative alpha is only applied to p, not to the kernel offset vector p double prime. And so by then equating these two, this expression here with this expression here, that then gives us an explicit algebraic perspective on what would be required for rotational equivariance to hold. So let's actually take a closer look at those two forms of the diagram and equate those two expressions and see what we can end up with. Well, this is why I really like diagrams and looking at pictures of things, because it reveals really what's going on. So here you can see that the only real difference between the two is that the p prime vector has been rotated relative to p double prime, and that's because with one path through the equivariance condition, the one in where we did the rotation in the image plane, the kernel offset vector got rotated, but the rotation in the feature map plane, the kernel offset vector did not get rotated, and that's why there exists this relative angle between the two, and that's why you need this particular substitution in order to then simplify these integrals and work out what the condition is for rotational equivariance. I remember being really frustrated during my undergraduate degree as to why, certain substitutions were sometimes needed for integrals, and so I really like pictorial explanations like this one, because it reveals why certain tricks and certain substitutions are sometimes used for integrals like this one. Okay, so using that fairly intuitive substitution, we can see that the p double prime argument in v can get replaced with q negative alpha of p prime, and we can then just go ahead and factorize for the q negative alpha, and then in order for the left hand side and the right hand side to always be true for all possible images, it must be the case that the kernel satisfies this condition. So the kernel at point p prime must equal itself at the rotated point p prime, where the rotation of the angle alpha happens. And honestly, in a way that's kind of obvious. So I think with this picture we can make it really clear as to how we can satisfy that condition, at least one way that we can satisfy that condition. And I hope you can see pretty intuitively that this kernel is exactly the same as this one if it gets rotated by an angle alpha. And in order for that to be true, that kernel needs to have a certain n-fold rotational symmetry where the angle alpha gives you the same thing, basically, right? So it's kind of stating the obvious.